All right, welcome everyone to our presentation. My name is Daniel Osorio, and this is my teammate, Gregg Hamm. And on behalf of our team, we would like to introduce you to our product, OsteoPrint. So, just the outline we're going to be going through today. We're already through the introductions. I'm going to be telling you about the current market, what our product is. Gregg's going to tell you about the setbacks and the process improvements we were able to make over the past 8 months. Then we'll tell you a little about the material testing and the characterization and the future of our product. So the current market. Let's get right down to 3D printing. It's a revolutionary technology. It uses thermoplastics to turn it into a 3D tangible model. Now, it's currently used mainly by hobbyists and research groups, such as the university setting for custom lab equipment, and some industries for rapid prototype testing. But what we're focusing on is the medical market. Now, the medical market is having 3D printing integrated into it at quite a rapid rate. Now, our project may centralize around screws and plates, but it also can be applied to joint replacements, artificial bones, casting, bandages, and even sutures. So we look at issues in the medical field. Now, the current problem is that it's not customizable. We're all built differently. That's why it's mainly because that steel is the main material used for surgical implants. Now, steel can also cause an inflammatory response. It can infringe upon the bone healing fully, and we want a way to get around this. So, how can we help with our product? We need to make it stronger and non-toxic. Enter NCC. We need to make it customizable for everyone's unique requirements. Enter 3D printing. We need a way to move around a second surgery if that is needed. Enter biodegradability. And also we need improved osteogenesis and osseointegration. Fancy words, we need it to act like a bone. The hard part is finding a way to mix all of these things together. Enter our product, OsteoPrint. Now, as Gregg is going to be showing, this is a sample of our product in a demonstration. Now, we have a shin bone here that has been fractured. We would then use x-rays and 3D scanning to see what kind of angle we have to enter the bone at. We would then decide what kind of threading, shaft size, length, all customizable within a 3D modeling system that we make a screw right for you. So, moving on, we would show you a Venn diagram of what our product hopes to accomplish. And the way we want to accomplish this is through choice of our raw materials. So first up is Nanocrystalline Cellulose, NCC as we call it. It's a very wide researched and investigated nanomaterial. One of its most attractive options is the fact that it's biodegradable. It's made from a renewable resource, and it's non-toxic, much unlike other nanomaterials on the market today. Why did we choose PLA? Polylactic acid is one of the most used thermoplastics in 3D printing. It's also biodegradable, and it's also renewable, and it's also non-toxic. So the two go hand in hand. So as you can see, this handsome devil up here is working on our product. What we were able to do is make an array of composites from 1% to 5% to see how the mechanical strengths have been improved. We used a solvent casting method in order to ensure the highest amount of dispersity, rather than something like double screw extrusion. We were also able to make alterations to our process so it can be upscaled to an industry setting. I'm going to pass the mic over here to Gregg, and he's going to tell you about the setbacks and the process improvements that we made over the past 8 months. Gregg?
Thanks, Dan. So over 8 months, you can come through a lot of hurdles, and I'm going to go over some of the things we encountered and how we improved upon them. So first and foremost was the time-consuming synthesis of our material. Next, we had properly dispersing NCCs. As a nanomaterial, it's extremely important to get a good dispersion, else it won't work properly. Next, we have grinding of the materials, which also showed complications, followed by filament extrusion process and biodegradability testing. So first, I'm going to show you some of the improvements we made to our synthesis. Here's a picture of our apparatus setup right there. We first increased the amount of solvent used and reduced the amount of solvent evaporation. This saved material as well as time. We then increased the number of apparatuses we had going. We originally started with 1, and then we worked our way up to 3 simultaneously. Finally, we reduced the amount of polymer sticking on the side of the round bottom flask. We did this by increasing the size of the stir bars and the way we poured the material in. This resulted in a 300% increase in production and a 50% decrease in process time. Next, how we properly dispersed our NCCs. As we moved on to higher percentages, like 4 and 5%, we noticed that sedimentation was occurring and we weren't getting a proper dispersion. Ways we worked around this was to increase the width of the container used and the amount of solvent. We then applied heat during sonication. This extra kinetic energy allowed it to disperse more properly. So this resulted in a 100% reduction in sedimentation. There was no granules left over after the sonication process. And we also seen increased transparency in our composite. This visually showed us that the dispersion was getting better. So next we're going to move on to grinding. Grinding is an incredibly difficult process because once you get to a powder form, it's easy to lose material. So we found that by increasing the amount of liquid nitrogen we used while grinding, we kept everything cool and reduced any friction buildup that happened. Friction can cause melting, which then loses a lot of your granule and makes your work redundant. We then used the proper tools, such as this anti-static gun here, as well as a paintbrush to better gather the material once it was grinded. This resulted in a 99% recovery rate, which is really impressive. We were guessing we were going to lose a lot of it due to this process, and we also reduced the time it took by 50%. So now here's Dan with some material testing.
Thank you, Greg. So for our material and characterization, we had to focus on our primary goals. Now, as we've said a lot, increasing mechanical strength was a must. So what mechanical property we were hoping to increase was the impact strength. Our screws and our pins has to be able to withstand large impulses of energy. Now, this is why steel and titanium are so attractive. They're resilient, and we want to make a material that can measure up to that. So, our impact testing, this is the one we're most proud of. We only expected a 15% increase. We saw almost a 54% increase at 5% NCC, way surpassing our goal. Next, we moved on to Flexural Modulus. Now, we were thinking this was actually going to decrease. What we found is that it increased by about 5% to 2.8 gigapascals. Moving on to the Flexural Strength, we actually saw that our data kept within our error bars, meaning it relatively stayed the same. Moving on to the Young's modulus, we did expect a decrease. Now, this is because the NCC acted like a plasticizer, allowing it to be a little more elastic. And for our tensile strength, much like our flexural strength, it was maintained within the error bars. So the toxicity and biodegradability. We couldn't really test this in-house. So our sponsor, Celluforce, hooked us up with NatureWorks and allowed them to do animal testing through them for a similar product of PLA and NCC. Now their PLA wasn't printing grade, but it's made of the same material. Well, we found that there was no target effects within the animal subjects. Also, there was no bioaccumulation and it was inherently biodegradable, allowing us to know that it wouldn't harm you while inside the body.
I'll now talk about some of the results we've seen when we did biodegradation tests. So we wanted to test how this would react within the body. So we placed this in a PBS solution inside an incubator to mimic what it would be like inside the body. We didn't have a lot of time to do this, so we only ended up doing a 28-day trial. As you can see from the picture, the color of the polymer changed slightly. It got from dark to white. This shows that there was some degradation along the surface as it cleaned off the outer layer that was somewhat burnt. As we measured the mass, we didn't see that significant of an increase, or decrease, sorry. And that's because within 28 days, you're not going to notice that much of an effect. Ideally, we want this to degrade over 2 to 3 years as the bone heals, so 28 days isn't really long enough to do that. So we decided to test the strength as we degraded the material. So we decided to go with a 7-day trial, a 14-day trial, as well as a 28-day trial. So here you can see that the impact strength actually improved slightly. We believe this is due to swelling. As you leave it in solution, we believe that the polymer absorbs some of the PBS solution, which fills in some of the voids inside the polymer matrix. Next, we have the flexural modulus again. We see a decrease here, but only slightly, as noted by the error bars there. This is likely due to the degradation process. As something degrades, it's going to get a little bit more flexible, but this is as expected, and it was only slightly. Here again, we see a slight decrease. A common trend you're going to notice with all these graphs is even though it decreases, it begins to plateau near the end. We theorized that as we went into larger and larger trials, that it would remain consistent and eventually plateau out. So here we have Young's modulus, again, decreasing, but within the error bars. As these things decrease, you're expected to see the strength go down, but this wasn't significant enough to make it detrimental to our application. So the last thing we went through was tensile strength. Again, the error bars were really huge, and we see the decrease with the plateau effect. So everything went as we expected, and we were very pleased with these results.
So now we move on to customizability. It's not going to hurt you. It's strong, but can it be printed? That's why we did DSC testing. Now, we really wanted to know the melt transition temperature. And as we can see here for 0% NCC, the melt transition temperature is about 160 degrees Celsius. Now, most 3D printers operate about 200 degrees Celsius, so this is why it makes it a good thermoplastic. But if we moved over to 1% NCC, we see that the melt transition temperature didn't change. This is perfect. It means that it could be printed. However, you will notice that the peaks are larger. This means that the heat capacity increased. This would be a certain requirement needed for the 3D printer in order to keep the composite hotter for longer in order to melt smoothly. We see this trend is the same for 2%, 3%, 4%, 5%, and the volume of the peak doesn't change. 3D printers already have different parameters for different filaments that are being put in, and this would just be a different parameter for ours. So the cost effectiveness, this is the part that makes me grin. NCCs are $10 per kilogram. PLA is roughly about $2.25 per kilogram. We're only using it at 5%. So ours are going to be about $2.65 per kilogram. If any of you have seen our booth outside, those screws are only 5 grams. The cost of a surgery mainly goes into the anesthetics, the doctor's time, power to run the equipment. This is a drop in the bucket. And as our friend Dr. Jean says, he thinks it's a-okay. So now I'll throw it over to Greg to lead you into the future.
So one of the things we wanted to focus on in this presentation was where we would go further with this product. Obviously 8 months isn't a lot of time, so there's many things we wanted to do, but we unfortunately couldn't. So one of those things was cell cultivation on the implant. We wanted to test how cells grew on a material. How would bone grow? How would it form? And other things like that. Other things we'd like to see is controlled degradability. We researched that certain block copolymers could actually be used to control the rate of degradation, allowing for more customizability. Next would be different grades of the composite. We would experiment with different molecular weights. How would this work? And how would it affect the impact strength as well as degradation? And finally, a selection of different non-toxic polymers. There's many thermoplastics out there that we didn't try. PLA just seemed like the appropriate choice based on our consultant's recommendations. So one thing we really, really wanted to go moving forward, but unfortunately couldn't, was fine-tuning the filament extruder. We actually managed to make our product, we just couldn't extrude it into a filament form for 3D printing because of the extremely delicate process. Right there you can see the filament extruder we used. It's made out of wood. If we had the expenses and time, we'd love to use a professional grade extruder that could be used to properly make filament that we could then use. We'd also experiment with granule size. Right now we grind it into a powder, but we found beads worked a lot better when using this process. And finally, I'd also like to experiment with the exposure to heat. Since the heat capacity of our product is now bigger, we need a longer time in order to melt it the same. So next, we're going to move on to biodegradability testing. Like I said before, 28 days isn't enough time to properly test this. We'd like to do year-long trials, 2-year-long trials, to see how this actually degrades in the body and what kind of rates we're looking at. We'd also like to test the biodegradability rates of different amounts of NCC. Adding more or less, does that affect things? We don't know at this time. Literature supports that the more NCC you add, the longer the degradation will be, but we'd like to test that further. So some future applications we can see using this material that are outside of the medical field are, again, hobbyists, research facilities, rapid prototyping. Making a polymer stronger is beneficial to a lot of people, and especially when the cost is negligible like you've seen earlier, it can be used in a large amount of industries.
So we'd like to finish our presentation by giving special thanks, especially to Dr. Leonardo Simone. Thank you for being our consultant. Thank you for leading us through all of our problems. Andrew Finkel, you were basically a second consultant. Without you, we wouldn't have known the process. Charles DeCastle, Masao Ishii, Jen Coggin, Neil McNamis, you taught us how to use the equipment. You showed you were consultants about how to do certain things. And they're not on here, but we also like to thank Zach Young and Ricardo Guerrero. Thank you for helping us with our demo model, and thank you for helping us with our poster. So thank you all. Thank you for joining us. That's it. Do you want me to turn this off?
You can keep it on.
Keep it on?
Yeah.
Okay. Sure.
Questions? So for the purpose now, right? Like what's the materials used? Not NCC, right? But other materials. What are those?
The materials of PLA and NCC, like what are they used for currently?
I mean, now I guess NCC is not really used for this purpose, right?
Mhm.
So you're the one exploring this. But what materials are used for this purpose now?
NCC is currently being more heavily researched. I don't really have an exact example of what it's being used for in industry. But the reason we wanted to move towards this nanofiller is because it's biodegradable and it had so many positive qualities to work inside the body. So we thought it was the best way to go about it.
Currently, also surgical steel is one of the more popular things used, but unfortunately, that has to remain in the body. If you want to remove it, it requires second surgery, which is very risky. You're probably going to end up breaking the bone again. PLA alone could be used, but it's inherently not as strong. So by using our filler, we're able to make it stronger and also produce smaller screws that do the same job. A smaller screw would be less intrusive and therefore safer for the patient going forward.
Yes, Professor Chan.
Do you think if you use a microcrystalline cellulose instead of a nanocrystalline cellular, will you see similar results?
I would like to say that we would see a similar result since the two materials are close to being the same. However, I couldn't say conclusively that it would. That is one of the future aspects that we were throwing around that would be possible in the future after we explored NCC more so.
I also mentioned earlier the problems we had with dispersing the NCC. I believe that this would mimic microcrystalline cellulose because when you're not having as good of a dispersion, you then move on to the micro scale. As we made these materials, we found that the impact strength wasn't as good, it wasn't great. So that's why we focus so much on dispersing the material properly to gain the best benefits to the product.
That can also be improved further by using a more sulfonated mixture of NCC. Unfortunately, we only had what Celluforce could supply us, and we were very grateful for that. But if we could have a higher grade to have even more exfoliation, we believe that those numbers that you saw would increase, and the numbers that stayed the same would possibly increase as well.
Sorry, just
Yeah.
one more. So what is the size of your NCC?
I'm actually not too sure exactly the dimensions of it, but I know that it's on the nano scale. But I don't have those numbers offhand.
Yeah. They're on our MSDS, and we left them at the booth, unfortunately.
Yeah, sorry about that.
Safety first.
Yes, Professor Sue.
Will you comment on the effective lifetime?
The effective lifetime of
Effective lifetime.
how long the PL of our composite will last within the body?
No, effective failure lifetime.
Oh, failure line.
Oh, failure. Oh, okay.
Because that's basically what the implementation most of the implants do.
Yeah.
Yeah, exactly. So over the lifetime of the screw, we obviously seen that slight degradation cause a slight decrease in the mechanical strength. We unfortunately didn't have enough time to fully explore the failure. But we would expect experimenting more and more, we'd be able to control the rate of degradation, and hopefully it would slow it down to a point where failure would only occur after the bone's fully healed, and it wouldn't really matter at that point. It can then just degrade within the body and allow the holes to fill in with more bone material.
The other question is, most of the implant these days, as you can see, they're very shiny. The reason is they want to remove as smooth surface as possible. So the bacteria won't attach to it before you implant it. In fact, that's one of the major problems of metal implants.
Yeah.
So you are making a plastic, how do you polish the surface, making it so smooth that the bacteria cannot attach on it?
Now we thought about sterilization methods in order to smooth out. You're absolutely right. 3D printing doesn't have smooth finishes as much as steel does. And it does have a corrugated surface. So we would suggest that we use a supercritical fluid in order to sterilize it of all bacteria. We can't use something like steam or radiation because it might degrade our polymer. So supercritical fluid looked like the best choice. And as for the corrugated surface, we would these are going into hospitals, so I don't think they would spare the dime in order to get the highest resolution possible of the 3D printers. And if it's still needed to be corrugated even further, I'm sure there is a fine finishing process, or perhaps even dipping in a solution like calcium phosphate, which was another aspect that we wanted to add. We found literature finding that there were professors that were able to print calcium phosphate, so perhaps coating it in this material would not only help give it that smooth finish, but increase osteogenesis and osteointegration.
Any other questions?
From the audience, anything?
No, not. Let's thank the speaker.
Okay, thank you very much.